All right, in this quiz, we're looking at buffer solutions, and the first question is asking that if we have a buffer that's made out of two parts, so sodium cyanate shown here, hydrocyanic acid shown with its Ka, we want to know first the role of sodium here. So we have NaCN, HCN. Why do we need the sodium at all? And the answer to this one is that we cannot add the cyanate ion without sodium, that we don't just have negatively charged stuff existing in nature. Whenever we want something negatively charged, we need to have a counter ion to bring it to solution. The most common counter ion for a positive ion that you'll see is sodium or potassium, and that is the role of sodium in the cyanate here. We have solid sodium cyanate or a solution of sodium cyanate that if it was solid and put into solution, they would separate immediately, and in effect, this allows us to ignore the sodium. However, I wouldn't just jump to ignoring it. I would make sure that you know that it's a dissociation, it's always soluble, and that this sodium ion, once in solution, will be for the most part inert. Okay, so now we're wondering, well, what if we add sodium hydroxide to the buffer in part A? And keep in mind here that we have sodium again, and it's going to be the exact same thing with the sodium hydroxide as well. We want to state the reaction clearly of what happens when sodium hydroxide is added to the buffer and if it is not equilibrium. And so what we want to recognize is this is strong base that's being added to a buffer, right? The buffer is a weak acid and a weak base. When we add the strong base OH-, this is going to interact with the acidic portion of the buffer. And these are going to completely cancel each other out, no equilibrium effects right away, and the reaction we have is the following. We have a reaction that goes to completion, where the hydroxides are combining with the hydrocyanic acid, and we end up making the conjugate base and water. Okay, so now we want to do some calculations where if we have a buffer that's half sodium cyanate and half the hydrocyanic acid, what is the pH of this buffer? And I've included the Henderson-Hasselbalch equation on this exam as well, but remember also that this is one that's really good to be able to remember from memory and does kind of tell a story about what it is. And what's key to this is that the buffer, or any buffer pH, is going to be based on the Ka of the weak acid component. And in this case, that would be 4.9 times 10 to the negative 10. This is given in the initial problem. The pKa of this acid is going to be 9.31. And if we put in our concentrations for our sodium cyanate and our hydrocyanic acid, we end up getting the following, which gives us a pH of 9.31. And this is a really important state for this buffer, because when we have equal amounts of the weak acid and the base, the two components of the buffer, we have pH equals pKa. That's what we have here, 0.5 molar and 0.5 molar, and therefore the pH of the buffer will be equal to the weak acid's pKa. Okay, now we want to figure out, well, if we add some sodium hydroxide solution, what is going to be the final pH? And remember that you already have this reaction from the first part, and it's this one, right, from part B rather, where we have the hydroxide with the cyanic acid, hydrocyanic acid that makes the weak base, and H2O. We want to set up a reaction table here for which everything is in terms of moles. So initially, we're going to be combining the hydroxide and the weak acid. And in 750 mils for this concentration of buffer from C, we get that there's 0.375 moles of the hydrocyanic acid in this sample, and that same number of moles of the cyanate ion. And when we add hydroxide, this is the moles of hydroxide that are being added based on the sodium hydroxide and volume that's being added. These are going to cancel out, and we're going to form the cyanate ion, and we are of course going to form H2O, but I've put Na in these rows just to keep things clear that while this does form, it is not something that we need to calculate for this problem. Now that we've completed our reaction table, we have our new buffer composition, which we can take and use with our buffer equation. Note that we don't need to consider the volume here because the hydrocyanic acid and the cyanate ion are within the same volume, so those parameters will just cancel. We're totally good to use moles here. We go ahead and we plug in, and we end up getting a final pH of 9.34. We've added a small amount of base, that's the NaOH, the sodium hydroxide that's been added, and therefore we have a slightly elevated pH even though buffers resist change in pH, they still will change, and that's what we get for our final answer in